Okay, so how do we make progress? What did you guys do to make progress towards building this cost function? Those who went that direction. Allie, I'll take that as a raised hand.
Well, you have to use volume because I was confused because I thought like the function.
Go ahead.
Can I explain it? Well, volume is 16 feet cubed.
Okay, is that a changing or constant quantity? 16.
Constant.
It's constant, okay.
But the side, like the base and the top are changing.
Yes.
The dimensions are changing.
Yeah, because the dimensions can change, but we need to maintain this volume of 16. So x and h can change, but they need to change in such a way that we maintain a volume of 16. David?
Can I use volume to solve, or like to put h on one side and then equal something and put that into the surface area?
Okay, so the volume are going to be used to help us get the cost function in terms of one variable, right? Yeah, so again, the goal is this cost function. The volume is just going to help us. We said we need these functions in terms of one well-chosen variable, right? So that's what the volume will help us with. So how are we going to build this cost function? Patrick, any ideas?
I wrote down stuff that I knew with the volume of 16 feet cubed.
Okay.
And that volume is base times height times width. And
Okay.
this would be x squared times h.
Awesome. But remember, the centerpiece of this problem is the cost function. So how do we make progress towards the cost function? Did you do anything in that direction? Trevor, how about you? Did you make any progress toward a cost function? Yeah, you guys are fixed on the volume, but we want to minimize the cost. So really, the volume is going to help us. It's kind of a side thing. It's going to help us, but it's not the focal point. It's not the centerpiece. Okay.
I made basically like because each part of it has a different cost. I found the area of each different part and then sort of added them together with the various cost functions around them. So
Okay.
The bottom I said was x squared, would be the area of the bottom, and that has a coefficient of 2, so 2x squared.
Okay.
Plus each one of the sides, there's 4 of them, has just a value of 1.
Okay.
So that'd be x times h, so it'd be 4xh because there's 4 different sides. And then the top is also x squared, but that's 1/2.
Okay.
Because it's half the cost of that. And so
Just going to do something similar?
all of that together.
So yeah, so that would be assuming that the price per square foot was 1 on the sides.
Yeah.
And then you're saying that's fine. I mean that's right. So he was assuming that the sides had a price of 1 per square foot, and so therefore the bottom would have a price of 2, and the top 50 cents or half. Okay. So a way you can generalize that is just say, let's say the sides is k. So it can be anything, right? So if the sides are k, so this is kind of what he was saying. The cost of the bottom is going to be 2 times k, right? Per square foot times the total square feet, x squared. And the cost of the sides would be just your k times, this is exactly what he said, 4 sides, each has area xh. And then the cost of the top is going to be half as much times the area of the top. Okay, so this is as much as I'm going to give you. So, Brian Kirk, where do we go from here?
Take the I'd say h in terms of x.
Okay.
Or, I did it differently.
You got h in terms of x, 16 over x squared.
Yeah.
But so again, what's the focus of the problem, David?
To find the cost function.
Cost function.
So,
For minimizing cost, everything is about building this cost function. Yeah.
so if you have the surface area, which is 4xh plus, or basically the four sides plus the bottom plus the top, if you add them together, it's like the surface area with k is 2k times x squared for the bottom plus 1/2 kx squared for the top, and then
But
k.
but if we're it's correct. But if we've got the cost of all the parts and we want to do a cost function,
Just add them together.
yeah. So yeah, we're just gonna, so we don't want to revert back to surface area. We kind of use surface area to build those different cost pieces, right? Yeah. So if you build the surface area function, then it doesn't really work because different pieces cost different amounts. So that's why if you build it separately and build the cost for each part, then our cost function is simply what?
2.5x squared plus 4 each x.
So we're just going to add up all the costs, right? And that'll be our cost function. Okay, so I'm going to leave it at that. So I'm going to give you more time to work on this, okay? But we'll just leave this one here. Any more questions? So do you see how the volume, so you're going to build that cost function? You see how the volume relationship is going to help you? Then what will that help you with? How will this volume relationship help with the cost function? That is Ben, right?
Did you say Ben?
Yeah, sorry. Not sure. Ryan, how will the volume relationship help with the focus of the cost function? How does the volume help? What's that?
H in terms of that.
Okay, so how does that help with the cost function?
Then you only have to do one
And which variable will it be? Right. Oh, I guess we already did that. So, yeah. Okay. So, any other questions on this one? Okay, so it's not going to look exactly like this. So, the work you've done, you may have done very productive work that didn't look exactly like this, but it should be, the overall idea should be the same. Any other questions on this one? Okay, and then we had this one. So did you get the right picture, first of all? Okay, see some nods. Is this the right picture? Okay, so we want to make heads or tails of this. And so what I'd like to do is, because the rest of you had the pipe problem, and this one, and then we're going to do another one, all involving angle and trig. So I want to do like a quick trig review, okay, of angle and sine and cosine. I think that's worthwhile. Okay, so I'm just going to go fast. Can you see that? It's so bright back there. Okay, so what am I showing you here? Let's do this in black. Do green. Show up a little better? Okay, that's better. What am I showing you here? What's that? Unit circle? 3 circles, right? What are the radii of these circles? 1, 4, and 6. Okay? So, what am I representing by that purple bar right there? What's that?
The radius of the inner circle.
Radius of the inner circle. Okay, so what I'm going to do is, I'm going to take that, I'm going to peel it off. I'm going to peel off that radius and put it on the circle. Okay, what am I representing by this blue bar? Mason. What's that?
The radius.
Radius of the middle circle, which is what? 4. Okay, I'm going to peel that off and lay that as an arc length on its circle. Okay, what am I representing here? Oops. Jason?
The radius of the big circle.
Radius of the big circle, which is? 6. I'm going to peel it off and put it on its circle. Okay, obviously these have different lengths, right? Length of this arc is 1, 4,
6.
but there's something the same about all these. What's the same? There's actually, you can talk into 2 things that are the same about all 3 of these arc lengths.
The degrees.
Okay? So the angle, right? So the angle, which is kind of like the percent of the circle that it's going around, right? They all go the same fraction of a full rotation. Okay? So if the initial side is the x-axis here, and the terminal side is where the arc ends, they all sweep out the same angle or openness of those rays, right? And what do we call this angle? Anyone know? Remember? We did it a couple months ago. This is a radian, okay? So this is a radian. Let's turn on my... So this angle is 1 radian, whether I'm looking at the red arc, or the blue, or the purple. It's all it's 1 radius length of arc length, so it's 1 radian of angle. Okay, so this is, each one of these marks is marking off, that's 1 radius length, that's a 2nd radius length, so what am I showing you by this angle? 3 radians, right? This is 3. What's the radius of the purple one? 1. What's the radius of the blue one? And what's the radius of the red one? What is that whole arc length right there? 3. Okay, we call that S. S for arc length. What is this whole arc length right here? How many units? 12. And how about this? So, how do we get arc length from angle? S equals what? Right? So, R times theta. And so, the key is that it's the angle measure, but that's the same value as arc length measured in what? No. So you don't measure distance in radians, right? So what's that arc length measured in? So this angle is 3, which means it comes from the fact that this is 3 what? Radius lengths. Radius lengths. So the angle, so you got, this is important for that pond problem. That angle measure, theta, in radians you think it's kind of like the openness of the rays. How open the rays are. Well, that's the same value as, it comes from how many radius lengths of arc length. And in all cases, the red, the blue, and the purple, or any circle, this openness is 3 radius lengths. Okay, and so then if you want the arc length in the units of the radius, then you're just going to take that many radius lengths times how long each radius is. And that's going to give you the total arc length. Right? So that makes sense. So the reason this makes sense is when you think about theta as length, relative to the radius. So the number of radius lengths. Okay, so what is the now I want coordinates. So I'll bring it back here. What are the x and y coordinates of that point right there? Okay, so you're estimating? Yeah, you're estimating. Okay, that's fine. So estimating, he's estimating about 0.75 and 0.75. Okay? What if we wanted to know exactly what the coordinates of that point are? Yeah.
We take the sine cosine.
Okay, so we've just swept out some angle here, right? And which is which? So what about the x coordinate?
Sine.
She wants sine. Agree? Well, maybe it's a good thing we're reviewing. So what is the x coordinate of a point on the unit circle? 2 wants sine.
Cosine.
1 wants cosine. It's cosine. Cosine is x coordinate on the unit circle. Sine is y coordinate. Okay, so it's that distance right there, right? So cosine is the x coordinate, and the sine is the y coordinate. So the coordinates of that point are cosine, sine. All right, now watch this. Sorry, it's not straight. That's supposed to be straight. How long is that right there? How long is it?
The sine theta.
Sine theta. Jason?
It'd be 4 times.
4 sine theta. Both are correct. It's sine theta if it's measured in what? Radius length. So whatever this value of sine theta is, John Paul says about 0.75. Well, this is about 0.75 of its radius length too. So yes, it's sine theta in radius lengths. But it's also 4 sine theta in terms of these units down here, the axis units. Or in terms of just the fact that the circle has a radius of 4. Using those, the radius units, it's 4 sine theta. Okay? And what is 4 sine theta? In this triangle, relative to theta, what is 4 sine theta? Is it the adjacent side, the opposite side, or the... It's the opposite side, right? So what does sine theta equal? Opposite over? Y, so it's opposite over 4, okay? Y is 4 the hypotenuse. You said hypotenuse because you remember that, but I'm going there. Y is 4 the hypotenuse.
Length of the radius.
Yeah, length of the radius. So from here to here, that's just a radius of the circle, and that's 4, and that's the hypotenuse of the circle. Okay, so these opposite hypotenuse adjacent formulas they come from this fact here. They start from the fact that cosine is the x-coordinate of the point, and sine is the y-coordinate of the point. So now if you have a bigger circle, you're going to have 4 sine theta. 4 sine theta is the length of the opposite sine. So that's why sine theta is opposite over hypotenuse. Okay, and then this right here, what's this dimension right here? 4 cosine theta, which equals? That, this whole thing is 4 cosine theta. What is it? No, it's not equal to that over the hypotenuse. What is this right here? It's the adjacent side. Now if we solve for cosine, it's adjacent over 4, again, 4 being the hypotenuse of the triangle. Okay. So these are just the very, very basics that kind of we need to understand. This relationship of arc length to angle, and the basics of cosine and sine. Okay. So how was the pipe? You had to redo the pipe problem using theta as the angle. Do we want to talk about that one?
The island one?
Yes.
Yes.
Okay. So maybe now we have a little bit. So what was the point of my little lecturette here? That S equals what? R theta, and we think of theta as, how do we think of it? What's our notion of it? Radius length of arc length, right? Radius length of arc length, because that's the same as the angle in radians. Okay, and then also that sine is a y-coordinate, cosine's an x-coordinate, and from that we get the opposite over hypotenuse and adjacent over hypotenuse. Okay, so that was, I just wanted to show you the origins of all this stuff. So hopefully it sticks, because we need at least these basics in Trig to work with some of these problems. Okay. Any questions on that? Did it help to review that? Okay. So the pipe problem. Can I erase everything? Okay, there it is. So what's the goal of the problem? Somebody new. Zoo. What's our overall goal in this problem? To build what? A little bit louder, I can't hear you. One more time, I can't hear what you're saying. Did you say minimize the cost? Yeah, so to minimize the cost, what are you going to need to minimize the cost? What's going to be the goal of the problem to build what? Then cost function. And I specified that we want our cost function in terms of, what do we want our cost function? What's our input variable going to be? Patrick? Theta, okay? So we need to get the cost. We need to get a rule with thetas in it that's going to give us the cost of all the cable, having chosen an angle theta. Okay, how are we going to do that? So did you make some progress doing that when you worked on it? Allie, any progress?
I thought it would be something with tangent because of the triangle with the island.
Okay, here.
So I thought you need to know the length of the hypotenuse.
Okay, so let's call it Z. So the cost of Z, this amount of cable, Z cable, is how much? What's that?
2400
Yeah, 2400 Z. Okay, and we could call, let's call this X here. What's the cost of this cable? Jason? 1,200 what? I put X here. So 1,200 X. Jean Paul?
8 minus x.
8 minus X. Okay, so really the total cost is going to be what? It's going to be this plus this, but what's the problem? Yeah, we need thetas. So the question is, how can we get Z in terms of theta? And X in terms of theta. So I'm going to leave it there. So once you have Z in terms of theta and X in terms of theta, now this is now using those relationships we just talked about. You can do it. So if this is X right here and this is Z right here, what does X equal in terms of theta? What does Z equal in terms of theta? Based on our little review there of trig, you can do it. And then the total cost function will be? Yeah, those added together, right? The cost of the underwater plus the cost of the underground. Okay, questions on this one? Can you make progress now on this one? Anybody have a question? Okay, back to the pond. Last chance on the cable problem. To the pond. What was the original problem was to minimize or maximize what? Time travel, okay? So what's going to be our goal in this problem? What's that? Okay, so find the minimum time, and in order to do that, we need what? What's the centerpiece of the problem? Time function. So we have distances, and they gave us rates, right? A rate swimming and a rate on land. So how do we get time from distance and rate? Ryan? So let's just call this 50, whatever. It's just as an example, 50 meters, okay? And he's walking 4 meters per second. Fast walking, okay? How would we get time out of that? How would we get the time it would take him to walk 50 meters at 4 meters per second? So if we think about, remember our bars? So 50 meters. What takes him 1 second? 4 meters. So don't we want to know then how many 4 meter lengths are in 50? That will be the same as the number of seconds. So how do we get time from distance and rate? We want to know how many of these, what is it?
50 divided by 4.
Right, distance divided by rate is saying how many, for instance, how many 4s go into 50. That will be the same as the number of seconds it will take him to walk the 50 meters. Okay, so time function is going to be, in general, distance over rate. Okay, so now I've given you a hint here. What did we say arc length was? We said it was angle, right? So we can use that to help us, especially because what's the radius of our circle? It's 1. 1, what, mile? That's very convenient because now the angle is exactly the distance in miles. Because radius lengths are in miles, right? Okay. So what is his time walking then? What was the rate walking and the rate swimming?
Swim 2 miles an hour, walk 4 miles an hour per day.
Swimming, he does what?
2 miles an hour.
Walking?
4.
So, what's the time spent walking? Patrick?
Theta over 2.
He wants,
Theta over 4.
he wants theta over 4. Yeah, that's it. Because his distance is theta, and the rate's 4 miles per hour. So walking, it's going to be, you said theta over 4. And then we're going to add the time he spends swimming. Okay, so we need to, so David got an idea?
DE over 2.
What's that?
DE over 2.
Okay, nice, okay. So length DE over 2. And by DE, I mean the length from D to E. Are we done? Danny?
We need DE in terms of theta.
Okay, good. So we need DE in terms of theta. So we're kind of far from done here. We need to get this length in terms of theta. So how can we, Jessica?
I have a question. Since we're not. That's on this color.
It's possible to do it totally differently. What was your, do you have a different input variable?
No, I did it in theta.
Okay.
But I used the chord length first. So the part that you have labeled as theta
Mhm.
minus pi minus theta.
Right, so you said this was your theta.
Yeah.
Yep, it's possible too. That's another possible way to do it. Yeah?
Wouldn't you have to use like cosine of theta?
Where's that coming from? So maybe, yeah, maybe.
Because cosine is adjacent over hypotenuse, and we don't know the hypotenuse. So if you do.
So what triangle? So we need a triangle first. So what triangle are you envisioning there, Lizzie?
I'm envisioning one that's where b to e is the hypotenuse, and then if you just chopped down at e, like.
So we're going to bring down here.
Yeah. Then that. So then that would be just.
See, and this is what I'm confused about. If that's theta, then wouldn't your radius be 2, not 1?
Okay, so if this is theta, is this theta? Right there?
Yeah.
No, B to E is theta.
Okay, so David's suggesting B to E.
This is where I'm getting confused.
I think I got it.
Okay?
If you connect, you know, D to B is one radius, and then you know, B to the point.
Wait, start again.
D to B is 1.
D to B is 1.
And then B to the point that you drop down is cosine theta.
Is this cosine theta right here? So let's make sure we know. So which angle is theta? Is it this one, number 1, or this one, number 2?
It's EBC. Or 1.
What do you think, John Paul?
I think it's 1.
It's this one. Okay? And so this length right here,
Cosine theta.
and this right here.
Sine theta.
Okay? And so now we have the right triangle that Lizzie wanted. Okay, now for this one, here's what I want you to do. I want you to build the function. So listen carefully. This is to help you. So finish building the function in terms of theta. You're right there. I mean, it's like 2 steps away. Okay? Find, so we know to minimize time, we're going to do what? How do we minimize the time? Set t theta equal to 0. Agree with that? Jason agrees? Brian? No. Why not, Brian? He wants the derivative equal to 0. Jessica likes that. You want to change your mind, David?
Yeah.
Yeah, so you're going to take t prime, find t prime. So this is like mastery, right? Mastery. Okay, but don't algebraically find where it equals 0. So now then graph t prime with graphing calculator. And then what will you be looking for in the graph of t prime? Once you get a graph in graphing calculator, what will you be looking for if you wanted to minimize t theta? Ben, any ideas? So we're going to get this graph of t theta, and our goal is to minimize t theta. And so what would that look like in the graph, right? But we're graphing t prime. We're graphing t prime.
When t prime changes from a positive slope to a negative slope.
Not quite. Allie, what were you going to say?
Oh, if we're looking to minimize, we have to look for a minimum point where.
But we're graphing t theta. Remember, so we're graphing the derivative. What are we going to look at for the derivative for a minimum of t? Jessica? Yeah. So we want to look for the x-intercept, right? And if it's a minimum, Ben, you almost had it because you said you're looking for where the derivative changes from not positive slope to negative slope, but just positive to negative, and you have an x-intercept at 0, right? So it's going to be like, this is what we expect if we're going to have a minimum cost. The cost will be going up. This is the rate, right? This is the rate function. The cost will be going up, then the cost will be 0, then the cost will be going down. And so right there will be, sorry, Wrong way. Did I screw it up?
If it's so positive, then
Isn't it should be once it stops increasing,
Minimum means
when it stops decreasing. And starts to increase.
so if it's a minimum, then it's decreasing, so the derivative is negative, and then there's the minimum where it's 0, and then it's going to start to increase again, so the derivative's positive, right? So this is the kind of thing we're looking for when we graph t prime. We're looking for this kind of thing right here, where the derivative is negative or t is decreasing, then 0 minimum, and then t is increasing because the derivative is positive. So doing this algebraically is there's too many. It's attainable, but it's a little too complicated for us. Okay. Well, it's not too complicated for, but let's just go this route on this problem. Okay. Let's do a graphical approach. Okay, and then there's going to be, so you can work on all these. So I've given you, because I don't want you to just try them and get them about half or 3/4 done. I want you to really feel confident about all your solutions to these. So that's why I wanted to talk about them and let you keep working on them. And then I'm going to give you one more, which will have to do with angle. It's a nice problem with the distance between the tips of the hands of the clock. Okay. So just keep working on these, and I'll give you one more. Like I said, it'll be on Blackboard. See you tomorrow. What's that? Nope, not collecting them. No quiz tomorrow, okay? So, next quiz will be next Tuesday. Third exam will be a week from Thursday. Third exam will be a week from Thursday.
Is that pretty much to me like related rates and optimization, or how
Yep.
far they're back?
Yeah, related rates. And we actually had related rates on the last quiz, so it'll be optimization and new stuff from this week.
So I meant on the tests.
The tests, no, further back.
Okay.
Yeah, all the way back to when we started doing rate from accumulation. Because the end of the last test was we covered accumulation from rate. So now we started rate from accumulation.
I have a question.
Let me turn this off a minute.